Hi everyone. Thank you so much for having me and being here in the middle of a Friday afternoon. When I first logged on, there were a couple of people saying this is one of their favorite meetings, and I definitely enjoy being here every February. So I'll be talking about like my course structure at large and how I introduce projects and modeling activities in the classroom. Um, and for some reason, my slides aren't switching. All right. Um, so I'll give you some background about the course structure, and then go over like the modeling activity that I do on day one, three projects that I do throughout the semester, and then close with some overall strategies that I have to do modeling in the classroom. So I'm still trying to figure out why my arrow is not moving my slides, so sorry about that. There we go. Okay, how did this start? I had given a lot of thought on how to present DE content in the classroom, active learning strategies, worksheets, different problems, course design, etc. Um, but I also wanted to show my students how DEs might be used, and so I implemented projects early on when I started teaching differential equations. But what I found was that even my students who were really comfortable with the material were really uncomfortable with making modeling decisions. I think I have a lot of students that are nervous to fail, and so making modeling decisions and making assumptions did not come naturally. They wanted an exact right answer. And the modeling process in general was foreign. And so I realized I would have to take a different approach and kind of slowly introduce them to the modeling process. And so this figure on the right comes from a textbook that I used for a different course a long time ago, but I've pulled out this graphic to show them many, many times to show them the process and how we iterate through models and try and refine them and try and make them better.
अरे वाह
But they
आमचे
never,
भारी बड़ा
but
शुरू
they
कर
never
दिया इन्होंने।
they never reproduce reality perfectly. There we go. All right, so here's my course structure. My course has three group projects. They're each about 3 weeks long, and I scaffold this material in two different ways. One is through the grade. So each project is worth more of their grade than the last project. So this is taken from one of my syllabi. It's not always this way, but the first one is 5% of their grade. So really low stakes and just to get them introduced into the process. But I also scaffold the material in another way, and that's by slowly having them make more and more modeling decisions as the projects and the course go on. So the first project really leads them through step by step, and the second project they have um, maybe a specific context, but they have to make more and more decisions. And then the third project is a little bit more of a free-for-all. So I'm going to give you an idea of three examples of projects that I do throughout the semester. But this isn't done in isolation. We also do the modeling project in class. I'll show you the activity we do on the first day of class, and we look at a bunch of other different models as the semester goes on. All right, so day one, we look at population growth. And so this is just a screenshot of some of my class notes. And I have them start, well, first reminding themselves of some notation. If U is our population, what does U of 10 represent? How do we interpret the derivative? And usually they can come up with those things. So we're talking about rates of change. And then we get to this question about, okay, well, what if our population at t equals 2 is larger than our population at t equals 1? And I have them discuss whether they think that the rate of change at t equals 2 is larger or smaller than the rate of change at t equals 1. And actually, on day one this semester, I found myself telling a group, like, okay, pretend you're 10 years old and I asked this question because they were kind of hemming and hawing and saying, oh, it depends. And again, they didn't want to make a statement that might be wrong in some context. And so I was like, had to kind of have them put on a more simple hat and try and make that assumption. And so then we kind of talk about where we're sitting in the modeling process. Okay, we're trying to formulate a model, and we're also getting used to um, comparing population size versus his growth rate rather than population size versus time. And so that's another thing. We start drawing these pictures comparing U and U prime so we can start to get a feel for what a differential equation looks like. All right, and so then we continue on and we start talking about whether this population makes sense. I give them the solution. We don't know how to solve it yet. It's day one. But usually they kind of say, yeah, this a population isn't going to be infinite. We need to adjust this. And then we spend some time in class talking about carrying capacity. And so we end up drawing this, talking about if a population is above the carrying capacity, its rate of change will be negative. It's in between, it will be positive. And we come up with a new differential equation. And so in day one, they get to see one full iteration of this modeling process. And so this is a kind of activity that I do in class regularly. Okay, so now I'm going to go through the three projects that we're doing, and usually they're working on these a lot outside of class while we're doing some modeling projects in class. And this is just one example of a place I start. I get a lot of chemistry students in my DE class, and so one thing I do is talk about radioactive decay. And we start simple and just model one element decaying, and the project kind of leads them through this whole process. They've seen this before. They've seen it on day one. This is a population growth model, except now it's decaying to zero instead of growing. And so they're really comfortable with this. But then the project has them discuss why this might not be great because we've got a chain of elements. Element A is decaying to element B, which is decaying to element C. Um, and so then they add a layer of complexity. I asked them to model A decaying into B now. And so they've gone through one kind of discussing whether these results are precise enough. I like this project because it has them interact with systems early on without actually having to know anything about solving systems because they can solve for the first element, plug it into the next equation, and solve there. Um, and then we eventually, at the end of the project, get to, well, there's some rate in of element A. We have a three chain decay chain. We end with element C. And so they've gone through this modeling process multiple times, which I think is really good to interact with it. And it's not often you kind of go through more than just one cycle through there. And we kind of talk about at the end what the limitations are. Usually I have students that know much more about radioactive decay than I do. And so I learn a few things too as well. All right, figured out these slide changes. So we're getting a little smoother. All right. So project two is a bungee jump project. And this actually, the original one I got from CMEO's resources. And so it's from Gregory Tanner at Concordia Moorhead. And so that actually works out nicely. I'm in Minnesota, and so is Moorhead. And so he's having the students design a bungee jumper jumping from the tallest bridge in Minnesota. And this is during harmonic oscillators, so they're really familiar with the differential equations they're using. And they're given the height of the bridge and some information about the bungees and some safety measures. We don't want the people to hit the river. We don't want them to experience any negative effects from acceleration. We don't want the bungee to stretch too much. And so it's narrowed the scope of the modeling that they have to do. They know the model that they have to use, but they still need to make a lot of modeling decisions. So now they're getting their feet a little bit more, a little bit further into the water. They need to decide how long the rope should be, how wide the bungee should be, or the cross-sectional area, what the safety margin should be, how risky are they willing to be, what weights and heights they can accommodate in this bungee jump business, whether taking into account air resistance and energy loss is important. So the scope is really narrow, which makes interacting with some of these decisions a little bit easier because they don't have to come up with a new differential equation. They've seen it before, but they do have to make some of these decisions that they're not used to making. All right. So here's an example of part of the modeling decisions they have to make is they have to decide how to deal with switching from free fall to the bungee jump portion. And there are a lot of different difficult things about this. One of them is getting the initial conditions for the bungee jump portion from the previous model. So they're dealing with some piecewise problems here. But the other thing is they actually have to think deeply about this harmonic oscillator model because the way it's set up is that x equals 0 or u equals 0 is the equilibrium when there's no mass on the bungee. But that's usually not how they set up the model. Usually x equals 0 is the ground is the way they set it up. And so they have to think about how this model is actually set up and how they're going to adjust for that. So there's a lot more modeling decisions in this second project. All right, I'm taking a minute to talk about my edit to this project. This spring, I'm doing Barbie bungee. When I used to teach intro to statistics, we would do this with linear regression. And so this on the left is me bungeeing Barbies in my living room. I was doing this over January, and my husband thought I was going a little crazy. But I uh, got some data from using the tracker software to track how Barbie bungeed as we sent her off the edge with a rubber band. And so now I'm having my students actually test their model with this data. In the final day of the project, I'm going to give them a height, a surprise one, and we're going to actually test their models and see. We're going to have a winning group who can get Extreme Sports Barbie closest to the ground without hitting the ground. And there's going to be, I'm calling it a consulting fee, but some prize for the group that does that the best. And so now they actually get to interact with data, estimate the spring constant using the data, and then test how well they did that at the end. All right, and then the last project is choose your own adventure, but a little bit more structured. So students are allowed to choose to apply differential equations to a topic they're interested in, but it's a little bit more reined in to make sure that they have some success interacting with the modeling project. Modeling process, they're provided with a list of ideas and resources. There are still frequent check-ins and instructor support. So the way I do this, actually with all of the projects, the way I do this is each week that we have a project, they have a check-in that's due where I ask them a series of questions. Where are they at in the project? How is the group work going? So that if there's anything going wrong, I can kind of steer it early on rather than the day before it's due. And then for this, we also have project days in class. And so that because it's a lot more self-directed, I get a lot more face-to-face time working with these project. And then there are clear guidelines for the final report, how they should be interacting with the modeling process, discussing their assumptions, the limitations, etc. But I've really found that a huge difference from now that I'm scaffolding projects, a huge difference between before and after with how they interact with this final project. They're so much more comfortable being creative and making assumptions during this final project when we've kind of eased them into this process and interacted really frequently with the modeling process. And I've seen a lot of cool projects. I had a group model the moose and wolf population on Isle Royale. She had been backpacking there over the summer and was really excited to tell me all about her backpacking trip and use differential equations to maybe understand what was happening there. Somebody modeled a TikTok trend on campus and how that spread throughout campus. Somebody tried to model Taylor Swift concert attendance. zebra mussels, a population of zebra mussels in Minnesota's lakes, uh, and a zombie apocalypse. That's what this is supposed to represent. Somebody made up like a disease and a bunch of assumptions about how the zombie apocalypse worked and modeled it throughout um, campus, I think. So, and then they present these during our final exam period and are usually pretty excited to tell everybody what they did. Um, so in a quick like summary about how I approach modeling in my differential equations class, the first one is I model early, I model on day one, and I model really often. Um, and then I also emphasize that models are wrong. I've gotten some pushback on this statement, but I think for my students that are really, really nervous to fail, that's a really powerful statement of you're never going to reproduce reality perfectly. And so that's what iterating through this modeling process is for, is you can see whether your results work and then go back and repeat. And then finally, I slowly reduce supports. So the first project, I kind of bring them through step by step what they're supposed to do. The second project, they have to make more decisions. And the last project, they get to be really creative about what they're doing. Um, so as far as model early, model often, this image on the right-hand side is an activity I do in class that I got from workshop. I think it was at Math Fest that Kurt Bryan was talking about Newton's law of cooling and measuring data with a potato. And so in class, we're taking temperature data with a potato, and then on their homework, I actually have them fit the data with Newton's law of cooling. And the students have a lot of fun with that because there's someone assigned to yell potato every time we're supposed to take a data point. And so in that sense too, it just makes a fun class and starts to create community early on in class. Um,
Uh, just want to give a heads up, there's about 2 minutes left in the talk portion.
Perfect, thank you. Um, And so, really, the last thing I guess thing I have to say is that I had a team do the SCUDA modeling challenge this fall. And we met a couple times before it started, and he said, "Oh, this is just like our projects," which isn't true. It was definitely harder than their projects, but I think it's just a picture of how this scaffolding approach they got more and more comfortable with modeling as time went on. Um, yeah, thank you for being here and dealing with some of my trouble shifting slides early on. I'm happy to answer any questions.